Today's focus is going to be on chemical reactions and exo and endothermic reactions. All right, so the first thing that we're going to be talking about are properties of matter. Okay, so we already know that matter comes in solids, liquids, and gases. So now what we're trying to do is, can we further distinguish one liquid from another? Okay, and so from that, you base it off of their different properties. So if I looked at a glass of hydrochloric acid and a glass of water, both are clear liquids, but what properties does hydrochloric acid have compared to water that water does not, or water has that hydrochloric acid does not? So one thing you can do is you can look at physical properties, or you could look at chemical properties. Physical properties can be observed or measured without changing the substance's composition. So it's something that it's physical characteristic of it. A chemical property is actually something that could only be observed when you actually change what it's made out of. So you're changing the identity of it. So an example of a chemical property would be it is flammable. So in order to see if it is flammable or not, in that case, you would have to try to burn it. If I burned it, I would be changing what it was actually made out of. If I didn't burn it, then I would be testing once again. I could be possibly changing its identity. A physical property, you are not actually changing what it's made out of. So what you're saying is it is blue. By me saying that it is blue, I am not changing any part of it. I am just saying that it is blue. So here are some examples of physical properties, okay, and chemical properties. You will have to note all of these. So if you can't figure out in your head, oh, did I actually change the substance or did I not change the substance permanently? Then you might just need to memorize these. So a physical property, some examples are melting points, boiling points. Any phase changes. So anytime I am changing what state of matter it is, I am just doing a physical change. The reason being, even though it looks totally different, it is actually made out of the same stuff. So let's go to ice. If ice is melting, it is made out of H2O beforehand, and it is made out of H2O afterwards. So it has not made out any difference in what its chemical composition is. Another physical property is a color. So like saying that they have blonde hair. Blonde, any type of physical attribute is going to be considered a physical property. So color, you've got density. How dense is it? Okay, size doesn't matter, any of that doesn't matter. It will maintain its density. Okay, density. Malleability. Malleability, if I look at the word, it looks like there's a mallet in it. Malleability is the ability to be beaten into thin sheets. So if you think about aluminum, aluminum is a metal that is also malleable. Why? Because I can beat it into thin sheets. That's where we get our aluminum foil from. Conductivity. So does it conduct electricity? By running through electricity through it, it does not change what it's made out of. It is still, let's say copper wiring, it is still copper. It is conductive. Magnetism. Is it magnetic? How hard is it? Okay. Chemical properties, on the other hand, remember you're changing what it's actually made out of. So does it have the ability to rust? When you're rusting, you're actually reacting with oxygen. Decay, you're breaking things down. Burning, you are also adding oxygen. Fermenting, or if you ever see reacts with, those are great signs of chemical properties. All right, so let's try to identify if these properties of water are physical or chemical. So water expands as it freezes. What you want to think about is, are you changing what it is made out of? If it is expanding, you are just changing its density, which means that you are not changing what it's made out of, so it is physical. Hydrogen peroxide can decompose to produce water. So we start with H2O2, which is hydrogen peroxide, and you guys should know that water is H2O. So did I change it to go from H2O2 to H2O? Yes, I did. Therefore, it is chemical. Water boils quicker in Denver, Colorado than at the beach. Okay, boiling is when you're going from a solid to a liquid. Okay, am I changing what water is made out of when I am boiling it? No, I am not. It is still water. It is just in the gaseous form, so therefore it is physical. When an electrical current is passed through water, elemental oxygen and hydrogen, read that wrong, are produced. Okay, so first off, we're starting with water, and then we are making hydrogen and oxygen, which is let's say like this. Okay, so if we're making hydrogen and oxygen, did I make something new if I start with water? Yeah, I did. I broke them up into H and O. technically should be H2 and O2, but we're going to just keep it, just think of it as hydrogen and oxygen. All right, so what is that? That would be a chemical change. Salt can dissolve in water. So if it's dissolving, this is also a key one that a lot of people get tripped up on, okay? Because you put the salt in it and it seems to disappear. So is that a chemical reaction going on or not? Well, if it is reversible, this is a classic sign. If it is reversible, meaning I can get the salt back, then it is considered absolutely physical, okay? So salt, if I can dissolve it in water and get salt back somehow, then it is physical. Well, how could I possibly do that? Thinking about it, you could just heat it up again. You could heat it up, evaporate off the water, and I would be left with salt. So that would be a physical change. Any type of dissolving or state of matter change is going to be a physical change or physical property. All right, now it goes to a physical change versus a chemical change. For you guys, there's not really much of a difference that I'm going to focus on between change and property. I don't really care. I want you to be able to identify the differences between physical versus chemical, okay? Physical, once again, you will change the visible appearance, but you're not changing the composition. So it is made out down at the atomic level. So with water or ice, if I go from ice to water, I definitely change what it looks like, but I'm not changing what it's made out of, okay? You only change the effects, changes that affect only the physical properties, okay, is a physical change. So once again, you're not changing the composition. A chemical change, on the other hand, you're making something new. You are changing literally what it is made out of. So instead of made out of H2O, I'm now made out of H2O2. Those are different things. These are examples of different terms that you will have to note. You'll notice that there's some carryover, like instead of saying boiling point for physical properties, we now just say boil. Okay, so these are kind of like the verbs of it. And then we've got chemical changes over here. Now note, this is also key. If you note, one is reversible, meaning physical changes, and chemical changes are usually not reversible. So try to think about that when you're trying to identify whether it is a physical or a chemical change. All right, there are 6 signs of a physical or a chemical change that you will have to note. And these 6 signs really help you out on identifying whether it's physical or chemical, because your background on this is very slim, if anything, actually. And so it's really important that you try to use these 6 signs. Now, my key is color change. So you see a color. We'll go more into these. But these are the 6 signs. If you see 2 or more of them, then I would go that it is a chemical change. So if I see both a color change and a gas produce, I would go that it is a chemical change. If I only see one, then I'm going to have to further think about it. The only one that is a definitive is this one. If you ever see a precipitate formed, okay, and you're like, what is precipitate? Oh, precipitation. No, it's actually not that. We try to mess you up a little bit, I guess. A precipitate is when I actually have 2 liquids. So I have a liquid, and then I add it to another liquid. And what happens is I actually get something that's cloudy in it. It looks cloudy, but that cloudy thing is actually a solid. That solid that's formed is a precipitate. Okay, and I'll show you a picture of one in a few slides. But if I add 2 liquids and I get something that's cloudy and a liquid, that cloudiness is actually formed by a solid, and that solid is known as a precipitate. If you ever get a precipitate, 100% it's going to be a chemical change. All right, so indicators of a chemical change. So you see a color change. So it's very hard to reverse, and one example would be, think about an egg. If you look at the egg whites before, they're like this yellow gooey thing, and then if you look at it after, they are white. Okay, so this would be a chemical change. Any type of baking or cooking or grilling will be chemical changes. Okay, you see gas production. So I see bubbles that are produced. So if I put magnesium into hydrochloric acid, what I see is a really big, strong chemical reaction, which is where I'm producing these bubbles. Now, it's really important that you understand that not every time you see bubbles, you have a chemical change. Why? Because a chemical change or bubble production could also be occurred like when you're boiling water, right? So are you boiling it, or is it actually undergoing a change of what it's made out of? Another example where gas is produced a lot is when, that you would be familiar with, is when you combine baking soda and vinegar. When you do baking soda and vinegar, That's called your volcano. So remember when you ever make volcanoes and you mix it together and then you get this big gas production, that gas production is because of the chemical change that is occurring between the baking soda and the vinegar. A temperature change, so it either will give off or absorb. So it could either feel hot or cold. As long as you see a temperature change, that is a sign of a chemical change. Light being produced. So if I see light coming out of it, like such as striking a match or a flame or fireworks, that is another sign of a chemical change. Here is the precipitate reaction that I was talking about. So a precipitate is this solid, once again, but when you combine two liquids and you get a solid and the liquid, which your really focus is the differences on the solid, that would be the precipitate. So if you look to the right on this graph, not a graph, but an image, what you see is you have two liquids. Okay, so I see these two liquids. What's really interesting is where they combine, you get this yellow precipitate, a yellow solid. Notice how it became cloudy. I can no longer see it. If I actually allowed this to settle, this substance right here, it would fall to the ground. I'm not actually making a crystal right here. It's not like growing up. It's actually just instantaneous picture. This will instantly settle to the bottom and you'll see this yellow powdery substance at the bottom. That yellow powdery substance is the precipitate. Now all precipitates are not yellow. It's just in this case, it's really apparent that we go from a clear liquid to something that yellow. So it's really stunning to see. All right, now let's focus on chemical reactions. So we focused on chemical changes, the signs of chemical changes. So remember, if you have any of those few signs, oh, the last sign that I want to talk about is irreversibility. If you cannot get it back, then it is more likely to be a chemical change. Now, when I talk about irreversible, like think of something decomposing, like a dead animal on the side of the road. So if I think about something decomposing, I ain't gonna get it back, right? It's not gonna come back to life. It ain't gonna ever look the same as it's decomposing. That would be a sign of a chemical change that is irreversible. But some ones also are irreversible, like that are physical. So don't just say just because it's irreversible, it is automatically chemical. If I rip a piece of paper, now you'll be like, oh, all you can do is tape it back, but it's taped. It's not actually together. That is irreversible. If I'm ripping, crushing, tearing, I'm not gonna make those things back. Like especially with a piece of paper, but I have not changed what the paper is made out of at all. It is still made out of paper. It is paper before, it is paper afterwards. It is just a smaller piece. So just because it's irreversible does not mean it is a chemical change. It is just a really good sign. All right, so now we're going to be talking about a little bit about chemical reactions. And remember, chemical energy is the energy that is stored in the bonds of the atoms. So if I change these bonds, then I change the chemical energy. Okay, so really, really important. We need to understand that this is a chemical equation. Okay, a chemical equation gives you your products and your reactants, and it tells you everything that's involved in it. Now, notice that we're not using words. That does not mean it is not a chemical equation. Okay. These are a simplified version that chemists and other scientists use to make it easier to transfer information as opposed to using words like water and hydrogen and stuff like that. We do their symbols, okay? For these types of reactions, what you need to understand is that we always are very, very consistent. First off, reactants are the stuff that you start with or are being used. So it's always what you react together. Products are what you produce. Look at the word produce. It's what you it's your product. Okay? These go together. It is the ending result. It is what you make. That is why a factory products or produces what? Okay, let's say they produce cars. Well, what is their end product? It is the cars. Okay? It's what you end with. How you read this is you always read left to right. It's exactly like how we read English. Everything to the left of this arrow, everything. So in this case, we just have one thing. Those are reactants. Everything to the right of the arrow, those are going to be products. So notice on this right-hand side, we have two products. How do I know that there's two? If I ever see a plus sign separates either two products from each other or two reactants. Okay, so if I had two reactants, let's say I'm adding A, okay, this would have two reactants. How do I know that they're two reactants? Because it's separated by a plus sign, not an arrow. An arrow separates your reactants, which are always on the left, from your products, which are always on the right. All right, so let's identify the reactants and products in each equation. Pretty simple. Okay, so we want to focus on this arrow right here. These are all 3 different problems, actually 4 different problems. Okay, so where are our reactants? Our reactants are always to the left of the arrow. So everything to the left, these would be your reactants. Okay, see, it's to the arrow, this is to the left, so these are your reactants. These are your reactants. These guys are your reactants. Everything to the right of the arrow will be your products. So these are your products, these are your products, products, and products. Literally find that arrow, everything to the left are your reactants, everything to the right are your products. All right, now we're going to be focusing on exo versus endothermic reactions. There are 2 big ideas that you have to think about. Number 1, it takes energy to break bonds. So if I want to break a bond, I have to put in energy. And then energy is actually released when bonds are formed. So to make bonds, it actually it releases energy. Okay, so there's more energy involved when things are separated than when they're put back together. Okay, so what you need to do to see whether it absorbs or releases energy, meaning exo or endothermic, you need to figure out if it takes more energy to break the bonds or to make the bonds. All right, so here's some examples of exo and endothermic along with their graphs. Okay, so exothermic, what I always think of that is well, X means out, but I always think of an exit sign. What is happening with an exit sign? It is leaving it. So energy in this case is leaving the substance. Okay, so energy is leaving it. It is exiting. Exothermic. Therm means heat. So heat is leaving. Okay, so anything with X is outside or leaving. So it's the outside, the heat is leaving. Okay, if I look at the graph, what I will look at is that we compare its potential energy, which is just how much energy it has. So energy used to break bonds, which is your reactants, is more than the energy required to make your bonds, which is your products. Now, looking at this graph, okay, notice that my reactants are higher than my products. So my energy initially is more than my final, which means I had to be able to get down to the energy that's involved in the products. I had to release that energy. So that is why it is an exothermic process. An endothermic process, on the other hand, is the energy used to break the bonds is less than the energy used to make the new bonds. Well, what that really translates to is that if I have reactants and I have products, okay, the energy in the reactants is less than the energy in the products. So how can I possibly, if I am trying to do this reaction, go from here to up here? Well, what I have to do is I have to absorb this amount of energy, which means I am an endothermic process. Okay, so that is endothermic when you absorb energy. Okay, really, 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 really important when you are trying to identify an exothermic versus an endothermic reaction. You need to identify what is the system, what is the surroundings. The system is the part of the universe that you are focused on studying. The surroundings is absolutely everything else. So if I am studying a hot pack, okay, whether a hot pack is exo or endothermic, the hot pack is my system because that is what I am studying. Okay, not this one. Okay, I am studying the hot pack, so that is the system. Everything but the hot pack, even including my hands, including the outside, is my surroundings. Okay, so you got to remember and think about what am I studying, what is, and then that's your system, and then everything else is your surroundings. All right. We can't observe the bonds breaking or making, so we can't observe like them literally breaking and making. So what we do is we check its temperature. So we're looking at whether the starting temperature went up or whether the starting temperature went down. If the surrounding temperature, meaning the surrounding temperature, decreases, okay, so I'm not talking about the system, I'm talking about the surroundings. The surrounding system decreases. That is an endothermic, and I'll show you visually why that occurs. Surrounding temperature increases. That is an exothermic. Okay, so we're not talking about the system here, we're talking about the surroundings. Why? Because the thermometer can only measure the surroundings, it can't actually measure the system itself, because it always is, unless it is the system, right? then you're studying something else, so therefore it's a part of the surroundings. Okay, so let's look at this. What is happening, whether it's endo or exothermic, okay? So if I look at, you always follow heat. Heat will either enter or leave, but you always follow where it goes. Okay, so it says what happens to the energy and the temperature in each reaction. So if I look at this guy down here, of course I chose the exact right color. If I look at this reaction down here, what is happening to this guy? Well, it looks like it's absorbing energy. So it is absorbing energy. And what does that mean if it absorbs energy? Its temperature will increase. So the system's temperature will increase. Now, if I asked you what happened to the surroundings, well, if this is your surroundings, what is happening to its temperature? Well, its temperature is going away, right? It's going into this, so it's actually decreasing. But the system's energy or the temperature is increasing for endothermic, okay? But I would notice my surroundings, it would decrease. All right, here's another one. So here is a system. And what I notice is that its energy is leaving. So energy is leaving. So what is happening to its temperature? If its energy is leaving, then its temperature is decreasing. All right. Now I want to identify if each reaction is endo or exothermic. Really, really important to identify whether the system versus the surroundings. So what is the system in this case? The system is this liquid. Okay, I'm going to choose a different color. System is the liquid. So I'm going to write system. This is the system, right? This is the system also. Where is your surroundings? These guys right here, this is your surroundings. Okay, everything but the system. All right, so identify whether each reaction is endo or exothermic. So for the first one, I go from my surroundings to 32 to 27. What I personally like to do is figure out if I'm going from 32 to 27, where's the heat going? Well, it obviously went down in temperature. So this point in the thing, which is outside of my system, went down. So what has to happen is that my temperature, my energy, had to go into the system. If it goes into the system and it absorbs energy, then what is this? This is endothermic. Okay, what happens as far as if you touched it, because you are a part of the system, it would feel cold. Okay, now let's look at this one. The surroundings goes from 22 to 27. So what had to happen? Well, energy from this had to go up to my surroundings, which means that this is exothermic. Okay, which means that it would feel, if my hand was out here, right, that's my beautiful hand, and I had the system releasing that energy, it would feel to me hot because I am a part of the surroundings. Okay, its system is losing temperature, right? It's literally losing, but it feels hot, so it's exothermic. All right. Hopefully you have a basic understanding of exothermic, endothermic, signs of a chemical reaction, which are those 6 signs, the parts of a chemical reaction, which are your reactants and your products, and then also physical versus chemical changes. All right, have a great evening.